So the hyperbola function or the hyperbolic function. The base function is y equals 1 on x. Sometimes you might see it written as the reciprocal function. So it's worth writing this square down. Give you a moment to do so, but I'm going to move on fairly quickly. Alrighty. So what I'm going to do is I'm going to unpack this function so that we can sort of get a sense of what it will look like. And what we do traditionally, I suppose, is when we're trying to work out the shape of a function, is we do a table of values, you know, x equals -5 to +5, something like that. Plot those values down on a graph, do a dot to dot to get a sense of it, and then to kind of figure out from there what the graph is going to look like. I'm going to do it slightly differently. I'm going to instead try and figure out what's happening to the graph by considering extrema, which means what's happening at the far right, the far left, the far top, the far bottom kind of thing of the graph. Then what's happening close by to the centre, critical values potentially like x-intercepts and y-intercepts, and you piece together the information to work out what the graph's going to look like. Now again, I could just show you this. I could just say, here is the hyperbolic function, and there's a picture of it. But by constructing meaning, you know, research is pretty clear that if you can construct the meaning for yourself, it actually sticks in your head a lot better. So here we're going to have a look at a few different bits of information to see what's going on. So number one, top right there. Now these next three screens I wouldn't bother writing down in your theory notes. This is really just exploring it. The next thing you can write down in your theory notes can be what the graph actually looks like. This is just trying to figure it out. So we've got y equals 1 on x, and I'm pretty confident that we can do this next thing probably in our heads. So you can see that I've got there as my sort of instruction as x approaches positive and negative infinity. And when a mathematician writes that, what they sort of roughly mean, I'll just make that a bit more sense so you can see it. What that roughly means is what happens as x gets really big, either positively or really big negatively. So to do that, you consider well, what happens when x is 10 or 100 or 1,000. So we've got 1 on 10, 1 on 100, 1 on 1,000, 1 on a million, 1 on a billion. What's happening to the value of y as I increase the value of x? Someone shout it out. Yeah, it's getting smaller, smaller and smaller and smaller and smaller and smaller. So as I increase the size of n, y is getting smaller. So we've kind of got this kind of thing happening. It's going that way. When will it hit the x-axis? What number of x can you give me that'll make y equal to 0? 1? 1 on 1 is 1, so y equals 1 when x equals 1 hasn't hit the x-axis. Never? So we've got a rather extreme opinion here. We've got something between 1 and never. If you think about it, Tian's right. Even if I chose a massively large number like 9.9 times 10 to the power of a billion, 1 on that is still going to be above 0. So we can't actually get to 0, but we keep on getting closer to 0. What about with the negatives? It's the same thing, right? 1 on -10 is going to be -1/10. 1 on -100 is going to be -0.01. 1 on -1 billion is going to be quite small. 1 on -9.9 times 10 to the power of 99 is going to be even smaller, but it's still not 0. So we're going to have the same behaviour. But on the right-hand side, as x becomes negative, y, although it's approaching 0, it's going to approach 0 from this side. Does that make sense? because 1 on a negative number is going to be a negative number. So it's going to be like this. So on the right-hand side, we're approaching like this, a bit like an exponential function from last year, if you remember. And from the left-hand side, it's a bit like an upside-down exponential function. It's going like that, but it's never hitting the x-axis. It's never hitting this particular value here. When we have a value that the function never crosses, what do we call that concept? Starts with A, rhymes with asymptote. Asymptote. Oh, genius, excellent. It's an asymptote, right? Asymptote. So we have a horizontal asymptote at, what's the equation for this asymptote? Good, excellent. Y equals 0. We don't have an asymptote at 0. We have an asymptote defined by the equation y equals 0. So that's what's happening at that extreme. The other extreme, or the middle, I suppose, is 0. What's happening as x approaches 0? So, Sunny's already said 1. We know that when x is equal to 1, we've got 1 on 1. That's for the fourth corner there. But what about between 1 and 0? So what happens if we have x equals 0.1? What's happening? We're going to have 1 over 0.1, and 1 divided by 0.1 is 10, right? What about 0.01? Well, 1 divided by 0.01, if you did that on your calculator, would be 100. Really quickly, I want to do this on the board rather than on the screen, but if I just do 1 on 0.001, that's 1/1000th, and then we know that's 1 divided by 1/1000th, and then we multiply by the reciprocal, and we get 1,000. So in other words, when the denominator is a fraction, when we go 1 divided by that fraction, we're just going to get a number bigger than 1. We're going to have a big number. And the smaller that fraction is, the bigger the reciprocal will be. Okay, so 1 over 1 trillionth is going to give me a trillion, etc. So as we approach 0, we are going to get a larger and larger value of y. And so we have this kind of thing happening. We have it getting bigger and bigger as it approaches 0. What about if x is negative? Well, if x is negative, then we're going to have 1 over a negative number. So it's going to be negative. But then we're going to, again, have a really huge negative number. 1 over negative 1 trillionth is going to be negative trillion. So we're going to have this kind of behavior as x approaches 0. Okay? So as x gets really big, y is approaching 0. As x gets really small, y is approaching infinity or negative infinity. Okay, but not beyond. Is that okay? Alrighty. We can't reach infinity. We can only aspire towards it, I suppose. And so we get another asymptote which goes down here like so. And the equation of this asymptote is excellent. That is not a function, it is a relation. X equals 0 is the equation for the vertical asymptote. So we've got all of these sorts of things happening here. We've got 2 asymptotes identified by considering what's happening at 0 and infinity. And then just a little bit of maybe putting in one more. We don't have any, sorry, stepping back slightly. Based upon slide 2 here and slide 3, can you see how there'll be no x-intercepts and no y-intercepts in the base graph? So the base graph of y equals, or base function y equals 1 on x, there are no x-intercepts and there are no y-intercepts because of those asymptotes getting in the way. It doesn't cross the axes at all. So there are no intercepts, which is what we would normally consider next, what's happening at the intercepts. But because there are no intercepts, we just consider something which is a fairly easy value to consider. So when x equals 1, we would have y equals 1 on 1. And so we would have one point, which is like 1, comma 1. Excuse me. And when x equals negative 1, then y would be 1 on negative 1. So it would be 1, comma negative 1 as well. So there's 2 more points. I'm so sorry. Drink of water. It's a good bit of video, isn't it? Hearing me clear my throat into the microphone. Lovely jubbly. Okay. So we can put all those 3 facts together. We can see that we're going to have this behaviour here and this behaviour here from here. So we're going to have this, and we can see there are some critical points here. 1, comma 1 and minus 1, minus 1 gives us an idea about what's happening here on the curve. So we can put all those 3 facts together to get to draw the hyperbolic function. Before I go to the next page and draw it in, I'll just ask you to maybe imagine in your head, or if you want to, on a bit of paper somewhere, or in the corner of your margin, draw what you think it's going to be. I'm okay if you just do it in your head. But do it though. Actively engage your brain rather than just passively taking in information. What's it going to look like? This kind of active engagement where you sort of either literally write it down, because that actually engages more parts of your brain than writing stuff down, or at least doing it in your head, is all about that constructing meaning for yourself. And if what I draw next doesn't correlate to what you've drawn down, well, there's a learning moment there. So all of that, if what I draw next does correlate to what you've drawn yourself, then that's a confirmation that your thought process is good. So either way, it's much better than just drawing the graph and saying, there you go, there it is. Okay, so these next 2 top slides there are worth writing down in your theory notes. So therefore, the base graph of y equals 1 on x, anyone feeling brave enough to draw it in and draw it onto my iPad? What do you think it might be?
Yeah, probably.
Who said that?
Go for it.
And it's all erasable if you get it wrong. So it's all words. See if he gets it right. I feel like I need to do a drum roll.
So probably something a bit like that, but a bit neater on.
Beautiful. Yep. Excellent. That shape there is really good. I mean, yeah, it's a bit wobbly. I don't care about that so much. People understand. It's a bit wobbly, but that's basically it. Hamish missed 2 pieces of information that is important for this graph. Can someone else fill it in? You want to fill it in? Bring out the big guns with Alex. Can you change colours? So it's really important that the asymptotes are drawn in, because they are part of the graph, right? They're part of the graph. So horizontal asymptote, y equals 0, and a vertical asymptote of x equals 0. Thanks, Alex. Okay, so all of that information needs to be put in. Okay, any questions so far? Alrighty. One other thing you could put in, but I don't see it as I wouldn't necessarily say this is something that should always be drawn, but I'm going to do it. But that corner there, basically, it's not really a corner, is it? But you know what I mean, is 1, comma 1, and that corner in inverted commas there is minus 1, comma minus 1. So this graph is symmetrical. It's got a line of symmetry that is diagonal along here. It's symmetrical that way. Okay, if there are no questions, I'm going to push on. I meant to say earlier, but by the way, I know this is going to be a fairly theory-heavy lesson, so there might not be a lot of practice time in this lesson, but we've got an hour and a half tomorrow. We're going to cover a new function tomorrow. but it's kind of similar to this one. So you'll have practice time and then a new function, then more practice time tomorrow. And I don't think we'll spend as much time with the new function because it's fairly similar to this one. And the other thing I mean to say, now that nearly everyone's here, sorry for the video, this is a bit of a tedious interlude for the video, is that yeah, I gave out the test on Tuesday because I'm trying to get into the routine of hand in, hand out on a Tuesday. So I handed out your assignment on a Tuesday, and then I sort of had a look at it like after class. So I didn't have it ready, so I painted and printed it in class, if you remember. And I looked at it on Tuesday, I went, oh, there's actually nothing they can do yet. They can't do anything until Thursday's lesson at least. So I gave it to you, and I went, oops. I put that on Google Classroom to say oops, but nevertheless, sorry about that. But I would have done it anyway, except I just wouldn't step in class. You can't do anything until Thursday unless you look at the theory, look at the textbook for theory. So, but yeah, but after this lesson, you'll be able to make a start on your assignment. So, sorry for the communication, but yeah, Tuesday is what I'm trying to keep a routine on. Okay, domain range. We know that Dix-Roy says the domain is the set of input values, which is the set of all x values. So we've got a pretty reasonable set of x values here. Just in plain English, because I'm going to write it down a bit more formally. In plain English, though, would someone like to describe what the domain is from what they can see? Just in plain English. You don't have to use fancy language. Just the domain is the set of x values. So what I'm saying is, what are the possible x values for the hyperbolic function? Em, you look like you want to have a crack at it.
I'll
Just waiting.
Yeah.
Okay.
So everything except 0.
Yeah, everything except 0. Good. Thanks, Shaka. If you have a look at it, it really is not constrained much. Every single x value, if I go along the x-axis here, whenever I stop, doesn't matter how far across I go, even past what I can see drawn here, if I go up, I'll hit the graph. So it's in. Similarly on the other side. If I go anywhere along here and go down, I'll hit the graph. So it's in. So it's all possible x values, except when I have x equal to 0, I'm on that asymptote line, which the graph never crosses. That's kind of the definition of it, kind of. So it's everything but 0. So the way we write that is like, so this is a more formal way of writing it, don't get me wrong. The domain is x is a member of, do you remember that R with an extra bar on it? That means all real values of x. Now, I want to give you this language in case you see it elsewhere. Backslash, not forward slash, backslash. That means left to right slash going downwards. Backslash means except for. And then I'm going to use a brace, a curly bracket, which says this is a set of numbers, and inside that set is just one number, which is 0. So that says x is a member of the real set, except 0. So all positives, all negatives, all decimals, all irrationals, all rationals, everything, but not 0. You could get away with this. That would be okay. The top one is a bit more formal, and I prefer it. I wouldn't mark you down for either of those. What's the range then? Who could write it in? I've got my iPad ready for you. The range, Dix-Roy, range is the set of output values. It's all possible y values that the function sort of exists for. Yeah? Say your voice. Say it's me, right? Also. Y is a member of the set of real numbers, except the value 0. Great.
Ignore the braces.
It's all good. We can all read what that means. Okay, so that's how you would write that formally. Again, very similar. I would accept y is a member of the real set, y not equal to 0. Okay, so in 415 we do try to formalise a bit more than we do in 315. In level 4 we try to formalise more than level 3. Okay, so that's basically it, and I hope that makes sense to you as well. That again, if I go up the y-axis, anywhere along that y-axis, if I go across, I will hit that blue line. Similarly, underneath the x-axis, I will hit the blue line. But at, excuse me, at y equal to 0, I'm going to hit the asymptote, the horizontal asymptote only. I will not hit the blue line, so therefore that's out of the range. Any questions before I move on? Okay, the next bit is just a little bit of an aside. I don't have to write it down because it's just something I'm going to probably say a few times along the way, and we might write a formalised definition of it in a second. So I'm just exposing you to the language right now. And the language I'm going to use here is that the hyperbola or the hyperbolic function is an example of a one-to-one function. Now, we know what a function is compared to a relation. Remember that a function is a relation where every input, every value of x has just one output. In other words, f of 3 has a specific value, 9. F of 4 might also be 9. F of 5 might also be 9. There's nothing wrong with that, but it's not f of 3 equals plus or minus 9. So every input has just one output, even if the output is the same. Okay, that's what a function is. A one-to-one function is like a stricter definition of a function. It's a stricter function. So in the case of a one-to-one function, for every input, for every value of x, there is exactly one output. There is only one output. So for every value of x, there is a corresponding value of y, and that is unique. So the hyperbolic function is an example of that because 1, 1 is the only pair. There's no 3, 1 or negative 2, 1. The output of 1 is only tied to the input of 1. The output of negative 1 is only tied to the input of negative 1. The y value of 1 only comes out from putting in an x value of 1. That's what makes it a one-to-one function. An example of a function that is not one-to-one, we call that one-to-many, is like your basic parabola. So here we would have, for example, 2, 4, and here we have negative 2, 4. Both of those things, each of these different inputs have the same output. That's fine, still a function, but it's not a one-to-one function because both 2 and negative 4 output positive 4. Okay, so it's a one-to-one function. And from now on, I'm going to start describing functions as one-to-one or one-to-many as well. So a parabola or a quadratic is one-to-many. A cubic might be one-to-one if it's like in an inflection kind of cubic. Otherwise, it will be a one-to-many. And a hyperbolic function or a hyperbola is also a one-to-one function. Alrighty. Moving on to transformations, and then we'll do a worked example and go from there. I'll need to use my lappy for that. Just going to have a quick look at Desmos and briefly go through what the transformations do. As I've said to you in previous lessons, we tend to hit transformations over and over and over again because the idea with transformations is that you can just remember the base shape of the graph, or it's on your formula sheet to be honest, and then if you are aware of how the transformations sort of affect the base graph, then you're good to go, right? So as you can see here, we have the base graph of the hyperbolic function. Now I've deliberately not put the asymptotes in yet, just so that we can play around with the transformations and get you to think a bit more. But we've got that shape as Hamish drew in, exactly like he drew, basically. A reflection, again, I'm just going to do this really quickly because I'm just conscious of time. have a think in your head about what you think should happen if we reflect about the x-axis. It's -1 on x. So reflection looks like that. It's pretty, isn't it? I'll take out the base graph though. So the reflection looks like that. Okay, it kind of makes sense. I'll put it back in again now. This bit here has been reflected along here. This bit here has been reflected across here. So it's basically, in the original graph, it's quadrants 1 and 3, and in the reflected graph, it simply goes to quadrants 2 and 4, reflected across. Questions? Okay, cool. What are the asymptotes for the reflected graph? Starts with exactly and ends with same. Exactly the same, yeah. So the asymptotes have not been changed, are not changed by the reflection, okay? The asymptotes have not been changed. Okay, next thing is if we have a look at this one here, which is A on X. Now, I deliberately got A is equal to 1. What happens when I increase A? What effect is it going to have? Use one of the transformation words. It's going to dilate, reflect, translate. Which one? Dilate. Is it a dilation in the direction of the y-axis or in the direction of the x-axis? Y. Okay, because the A, I'm going to do this on the board. I know that's not good for the video, but all I'm doing, I'll explain what I'm doing for the video's sake. The A, when you've got y equals A on X, the A can be pulled out of that like so. A multiplied by 1 on X. So you can see that the A actually is the dilation of 1 on X. It's not the dilation of X. That would be in the direction of the X-axis. It's a dilation, it's A times 1 on X, the base function. So it's a dilation in the direction of the Y-axis. Okay? So just be mindful of that. That A on X is the same as A multiplied by 1 on X. Same thing. Okay? Same thing. Alrighty, so as I increase this, it should stretch away from the X-axis. And you can kind of see it doing that. It might look a little bit weird, but can you see it's almost like being peeled away from the X-axis? It's being stretched up ways, like so. Of course, if A is negative, then we have a reflection as well, but it's still stretching away from the X-axis. And as usual, when we go down as far as between 0 and 1, positive or negative, we have it pushing towards the X-axis. So it's in the direction of the Y-axis, but it's pushing towards the X-axis. So it's squeezing itself down to the X-axis. So it's dilating in the direction of the Y-axis. Is that okay? I'm trying to push on as fast as I can. Okay, this next one here, A over X minus H, what effect should that have from your understanding of translations? Yep, it'll go left or right. So this is a dilation of the input. Sorry, beg your pardon, a translation of the input. So as H gets bigger, oops, that could be useful, couldn't it? As H gets bigger, it translates over that way. Remember, it's X minus H on the bottom here. So X minus 9 means it's going 9 to that way. And X is negative, it's going that way. I'll put H back to 0 because I forgot that I should just say really quickly what's happening to the asymptotes here. Same, yeah, exactly the same. So they haven't changed. What's happening to the asymptote with this one? Same? No. Which one's changing? The vertical asymptote, the horizontal asymptote, or both? Yeah, the vertical one's changing. So the value of H affects the vertical asymptote. The value of H affects the vertical asymptote. And I think it might be a bit of a no-brainer to suggest what's going to happen here. So here's my graph here. And so guess what the value of K does? Up and down, and that affects the horizontal asymptote. So if I put the asymptotes in now, you can see the asymptotes are just defined as X equals H and Y equals K. They are the equations of the asymptote. And you can see that as I change these things around, The value of K changes the position of the horizontal asymptote. The value of H affects the position of the vertical asymptote. The value of A does not change the asymptotes at all, and making it negative also does not change the asymptotes either. So they are the effects of the transformations. Right, any questions? Alrighty, I'm going to use a very specific asymptote now. So I'm going to make A equal to 12. I'm going to make, I'm going to add in, I'm just going to do it here to be a bit rough with it. I'm going to add in a number here, which is 4. And I'm going to add in K equal to 2. Where's K? K is equal to 2. And so I'll make H equal to 8. Okay, so H is equal to 8, but the equation is A over 4x minus H plus K. Have a look at the asymptote. We've got the asymptote at 5, 6, 7, 8 here. Okay, so is that okay so far? Yep, cool. So I just wanted to point out what we've drawn here. I can't remember if I've got this on the screen or not. Let me have a look. So what we've got here is this function here, y equals 12 over 4x minus 8 plus 2. And what I just wanted to point out is that if what we could do is we could do, if you remember when I was talking about the cubics and quadratics and talking about a dilation of the input here of 4, so that would be a dilation of factor 1/4, right? We can sort of do the same thing as we did in the cubics and quadratics, and that is we can factorize out that number. So I'll just do that now. I'll do it in a different color just so you can sort of see where the bits are. I can take out a common factor of 4 here. I've deliberately chosen the numbers so they are tidy, but I didn't have to. That's 4 outside of x minus 2 plus 2 here. And then I can cancel the 4 and the 12. I can cancel the 4 into 12, goes 3 times. And I can make that 3 outside of x minus 2 plus 2. So I can always cancel out a dilation of the input. I can always take out a common factor and cancel it out. So I just wanted to highlight that. So if I've got this graph here, y equals 3 on x minus 2 plus 2, what's the horizontal asymptote? I'm not going to go back to the graph. Based upon you just seeing the graph, what's the horizontal asymptote here? Is it y equals or h equals?
Y equals 2.
Y equals 2, good. And what about the vertical asymptote? X equals 2, yep. So we can use our values of h and k in order to denote what the asymptotes are. I accidentally picked the same asymptotes here, but again, just to scroll to the top here, the asymptotes are x equals h, y equals k. X equals h, y equals k. So all we do is identify the h and the k, just like we've done in other graphs. And we can say, well, it's x minus 2, so we've got h being 2, and therefore x equals 2. And then we've got y equals 2 being the k value here. Personally, I kind of say, well, the vertical asymptote is kind of the impossible value for y, and the impossible value is found by setting the denominator equal to 0 when solving. So here you can see x minus 2 equals 0 gives me x equal to 2. Here you can see that 4x minus 8 would be equal to 0, which means that 4x equals 8 and x equals 2. So whichever format you've got it in, if you just set the denominator equal to 0 and solve it, that will give you the vertical asymptote. But yeah, if you put it into this format though, you just need to read off the value of h, whichever way works for you. Okay, so now that we've done that, let's talk about the domain and range. What is the domain of this new function? Is it still all real x except for something? Yeah. So it's x is all real numbers. But what are we excluding now? Yeah. Except for 2. What about the range? Same deal, isn't it? Except for 2. Again, that's just a coincidence, right? The fact that the horizontal and vertical asymptote are 2 happens to mean that the domain and range set is the same. But that's just a coincidence. It could be different values depending on h and k. So generally speaking, the domain, I'm not going to write this down, but the domain is going to be all real x except for h, and the range is going to be all real y except for k. Now it has intercepts. Okay, because we've changed the asymptote, I'll just quickly go back to the graph again, which I know is not quite right now, but don't worry about that. Because it's got asymptotes, we now have the capacity to have a y-intercept and an x-intercept. Okay, so you need to work out what that y and x-intercept is, and I'm not going to get you to do it because of time, but I'm just going to say the intercepts are worked out as usual. All right, so for the x-intercept, you set y equal to 0 and solve, and you can do that. If you did that, you would get a 0.5, 0. Again, you can solve it for yourself. I just don't have time now. For the y-intercept or intercepts, it's not going to be intercepts, you let x equal 0 and solve. And that would give you 0, 0.5. This is coincidence again that they happen to be the same sort of number here, 0.5, 0, 0, 0.5. That's a coincidence because of the way I set up the graph. Okay, they don't always match like that. But I wanted to just point out that even though it's a new graph type for you, the procedures are still the same. Apply the transformations like you did at the start of the lesson before you even explored the hyperbolic function. Okay, you can apply the transformations. You can use the knowledge of the transformation in order to work it out. And the last thing is it still one-to-one? And the answer is yes, it is. It's still one-to-one. Just because we've shifted it around and stuff, again, ignoring that I haven't quite got this graph set up properly, there is still, for every x value, there is exactly one y value, and that y value doesn't appear anywhere else in that set of pairs. Okay, so the y value maps exactly to one x value as well. And that's it. Now, where we're headed next, I'm going to pause the video because you don't need to hear where we're headed next.